Good morning, everyone, and welcome to your first Half Day Wednesday. My goal is to make this as quick as possible so that you can be off and on your way and enjoy half of your day. So, for today, this is the unit map for our unit. So far, we've made it to just around here. We've started looking at electromagnetic waves. If you were in a period A double class, you made an electromagnetic spectrum. If you're in a period B double class, then you watched the video 4, but didn't have to turn in the electromagnetic spectrum because you had one fewer class day than the other. In any case, electromagnetic waves travel at c, a number that's so important it gets its own speed, its own symbol. It's the speed of light in a vacuum. When it goes into a different material, there's more objects, in this case particles, atoms, electrons. There's more things in the way, and so that means that the light wave has to slow down. Electromagnetic waves are waves that are made up of alternating electric and magnetic fields. These include radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gammas. These you should know in order from low frequency to high frequency. If you don't know them in order, I suggest coming up with some sort of acronym. Like, think about how visible light is broken up into Roy G. Biv. Infrared is below red, ultraviolet is above violet, but everyone knows Roy G. Biv from when you were a little kid. See if you can come up with your own acronym to help remember radio, micro, infrared, visible, ultraviolet, X-ray, and gamma. We did some practice calculations using the speed of light, so our 3 times 10 to the 8th, but using our original speed definition. This equation would be using the speed of light in order to find a distance that light travels in a certain amount of time. Since light is an electromagnetic wave, we could also use the wave equation. We could substitute c, the speed of light, for v, and solve for either wavelength or frequency. Note that this means you need to be really super comfortable with scientific notation. If you are not, I would suggest go brush up on that first before you do all those problems. We know that the speed of light in a material is slower than through a vacuum. Well, how much slower is n, the index of refraction? If you didn't get a chance to watch the Homework 10.3 key video, I do suggest to do that. In that, I talk about how index of refraction is a number between 1 and about 2.5 that's unique to the material. So for instance, water's index of refraction is 1.33. And the higher this number is, the higher n is, the lower the speed of light in the material is. So something with a high index, like a diamond, would have a low speed of light. Now see, the speed of light in the vacuum doesn't change, but the speed of the light in material will slow down. And since the speed of light changes as it enters a new medium, this gets a special name. This is called refraction. Refraction is when light enters a new medium, and it changes speed, so therefore it changes wavelength. When the speed of light changes from 3 times 10 to the 8th, that's 1 times 3 times 10 to the 8th, when that speed of light changes in the material, it slows down. Now it's only going a fraction of the speed of light in a vacuum. It slows down in this new material as I make the index larger. Increasing the index makes it slow down. And that makes it also make the wavelength smaller. Notice the different distance between subsequent crests in this picture. In this case, because the crests are closer together, the wavelength is smaller. Another thing to notice is that means that the frequency of light doesn't change. The speed and wavelength change, so the frequency stays the same. But guys, that should be inherently obvious. When a wave goes from one material to another, the frequency, which you and I hear or see as color, doesn't change. When I look outside through a glass window, that doesn't make everything look like a different color. If the red tulip outside were red, that frequency stays the same, so the color stays the same. The direction does change as well, and on Thursday you and I will work on Snell's law, an equation that actually uses the incident and refracted angles in order to figure out the index of refraction. For now, it suffices to note that the direction changes. In whichever material is faster, the ray of light makes a larger angle with this important measuring mark called the normal line. The normal line will always be used for measuring angle. In this case, please note that that means the angle we're concerned with is not between the glass air boundary, not where these two lines are meeting, but rather where the normal line and the incident ray are. In whichever material the light is faster has a fatter angle. In that case, that's what, like 50 degrees? 45? Whichever one light is slower in has a slimmer angle. That angle is only like 28 degrees. Now, refraction sounds a whole lot like another vocab word, one we talked about last unit, one that's really similar to something you should be familiar with. Well, that's reflection. To tell them apart, when light goes from one medium to another, and it changes wavelength and direction and speed, that's called refraction. But actually, notice that there's a reflection as well. Reflection is when light hits a boundary and bounces back in the same direction from which it came. And when I mean the same direction is I actually mean the same angle from the normal line. So a light ray that went in at, 45 degrees goes out at 45. A light ray that goes in at 80 degrees will reflect also at 80 degrees. So notice that both reflection and refraction happen when light hits a barrier. When light hits a barrier, some of it travels into the new material and some of it reflects back into the old material. But to close this off, keep in mind that you already know that light both reflects and refracts. You've probably noticed when you've looked out a window that you not only see your reflection, but also the refracted light from behind the glass. Light from behind the glass traveled through air, then glass, then air, then reaches you. That refracted light coexists with the reflected light, and our brains have learned to tell them apart. So, take today's quizzes now that you've reviewed everything we've known from the unit so far. Tomorrow we'll work on Snell's law and total internal reflection on Friday. Then we'll get to diffraction and absorption and emission all next week. Best of luck!